Hello everyone, welcome to our class. Today we're going to talk about the virtual memory, these special memory hierarchies in this class. So let's take a look at what's a virtual memory and what's the difference between a virtual memory and a physical memory. Okay, so traditionally we have a physical memory here, and we have a cache, we have a registers, so we have a cache here, we have registers here, and we usually just load the data from physical memory to cache to registers. Then when we want to use it, right? So in this case, what's the address, memory address we use in this physical memory? If you understand everything we talk about in other videos, you should know actually the physical memory just use a physical memory address, right? So for example, if we want to load 4 bytes from here to here to here, this physical memory 32-bit information will be do some conversion. For example, we will use the mod or something to find a set, or use a tag to check what's a block we want to load to the cache. Then we use the register to access this data, right? But the memory address itself is actually mapped to the memory address space. So if we have a 4 gigabyte memory space, then which means for each byte we have a specific memory address to match each byte in the memory. So we call it physical addressing, okay? So this is a traditional model for your computer. But here we want to talk about a new model. It's called virtual memory. First of all, why we need virtual memory? Because think about that. If you have a program with this physical memory, and you have another program want to use the same physical memory, so you will see let's multiple different programs, just 2 programs that use the same physical memory. That might be a conflict. For example, one program want to use this physical memory here, another one want to use here. So there's a conflict, right? If there's a conflict, how you deal with this conflict? It's not easy. Definitely, it's not easy. So you probably need to, when you want to run the second process, you need to turn off, save all the information in the first process, or you can just not allow the second process to start until you finish your first process, right? So this is definitely not a good model for a current multitasking operating systems. But this physical address strategy still used in some more like a small device, like a micro embedded systems. They are still use this physical addressing stuff. So it still work, but usually it's work in a smaller device to work on some we don't really want to do some multiple tasking the process, this kind of concepts device, okay? So for modern systems, what we want to do is we want a smart way to manage this. So actually, how to do this? If we have 2 processes, we don't use physical addressing, we use virtual addressing. So still, each process has a 32-bit a memory address to support it. So the first process has this value, the second one might have this value here. And if we want to load the data from the first one, we load to here. If we want the second one, we load from here. But because the virtual memory, they are independent to each other. They are stored in the process itself. So each process has its own virtual memory. So you don't need to worry about the conflict, right? And here's the thing. If this is virtual memory, this is not actual physical memory, which means we cannot just load this data from virtual memory to the cache. We need another layer here. It's called physical memory. And the cache should be here. So you can see actually what we want to do is we have a virtual memory for each our process. We also have a physical memory here. When we want to get the data from this virtual memory, we load the data to this physical memory. If we want to get data from another virtual memory, different process, we load to this physical memory. Then we use a physical memory to load this data, to continue to pass this data to the cache, to registers. This is the idea of virtual memory. Okay, so for this idea of virtual memory, let's definitely one very critical part is how to deal with this. So when we load the data from physical memory to a cache, we have some like a methodology to decide which set we want to load this data, what the block we want to load this data, right? Here is a set. We need to figure out what's the data, where, and how to convert a virtual memory address to a physical memory address. Also, there's another part we need to consider is that because right now we have multiple virtual memory, if the data is over than the physical memory size. For example, we have 10 virtual memory and we just use like half of this virtual memory in this process, which means we get more data. Actually, the data is more than the physical memory, right? So in this case, how we deal with this? So when we use virtual memory, actually, it's a very interesting way to deal with this situation is that we don't just use the physical memory, we also use disk. So for some data here, we load to physical memory. But for some data here, if we don't use it now, they are actually on the disk. Because disk is definitely larger than the physical memory, right? It's definitely larger than physical memory. So we use a disk to support, become a supplemental memory space to support physical memory. We will talk about details later, okay? Since the data can be stored on a disk, the secondary storage for these virtual memory systems. So let's look at what's the details in this virtual addressing and also the physical addressing, okay? So right now, because we want to use these virtual memory systems, so it's very important that we have a virtual address, which is inside your process. So for this virtual address in your process, you have virtual memory. Virtual memory has its virtual address. We need a way to convert the virtual address to a physical address. So this physical address and virtual address, imagine that the virtual address is actually the memory address of your virtual memory in your process. A physical address can be in your physical memory, which is your RAM, or it can be on your disk. Okay, why? Because remember, the data, if you want to use the physical memory, your RAM to store all the data it does not like possible if if we want to support multitasking this a lot of process together, right? So we use a disk to support, which means we need to figure out, okay, is this physical address is belong to a RAM or is belong to a disk? So to help us to generate do this conversion, we need a device. So actually, that's a hardware device called memory management unit. This memory management unit can help us to convert your virtual memory to a physical memory. And this physical memory address, virtual memory address to a physical memory address. And this physical memory address, if the data is on your RAM, on your physical memory, the physical memory address will map to the physical memory place. If the data is on the disk, the physical memory address can also help us to find the data on your disk. Okay, so this need a lot of support. You need the MAU, this device. Also, CPU need to do support. Your operating system need to do support to make this happen. Okay, so if you understand this, what's the virtual memory? Virtual memory is actually it's virtual, definitely it's virtual. The data stored in your virtual memory is not just stored on physical memory, on the RAM. It can also be stored on disk. Okay, so one process, if this is inside the process, in process, if you have data here, you have data here in this process, you can see this data actually stored in your RAM here. But the data here is actually stored in different place on disk. this is how we actually use this system to support. So we got array of n contiguous byte-sized cells stored on disk. And if we want to use this data, they will be logged to the RAM. So you will load this data to the RAM. We call this cache. We cache the data to the RAM. So imagine that in this case, we actually use the physical memory of RAM as a cache to support this, right? If you remember in other videos, we load the data in your physical memory, in your main memory to the cache. Then we load the data from cache to register to do the computation. Here is the same. We load the data from disk to your RAM. Then load the data from your RAM to the cache. So in this case, the whole concept is like the RAM is actually the cache for this memory, right? So this is a very important idea here. The data on disk, they are still the data. So they are allocated data. But this data might be like resided on disk, and until we want to use that, then they will be logged to the cache. So if we want to do that, there are definitely some details we need to pay attention. One most interesting and most important detail is about how to partition the block, how to partition the data, the chunk of data in your memory. We use the same idea as a cache. We use block. So when we want to load the data from your disk to your physical memory or RAM, we load a whole bunch of block. We call it virtual patch. So we load a patch with a size P, and of course we know we like two power, like a 2 to something power of 2 to represent. For example, it can be 64 bytes. This can be 128 bytes. So this P is your page size. So this page size is your virtual page size, but it can also be your physical page size. So imagine that you have a disk and you also have a physical memory. If you want to load the data from disk to memory, you load a block, whole bunch of like page to a physical memory, right? We call this a page size. If we want to load, we just load a whole bunch of data together, okay, from the disk to a physical memory. If we want to store the data, we also package the data in a patch to store on disk, because it's easier for us to load the data to the physical memory. Then we can take a look of what's the memory and disk, the difference between the data in the memory disk or somewhere. If I have a data here, which is data, this data is not generated. So we try to run a program and we haven't generated a result. This is just totally new data we generate from a program. If this data is not in the memory, not in our disk, we try to get the data from memory and disk. What we do? We try to allocate it, right? We allocated the data on memory. Usually, if we don't have disk, we allocate data stored in the memory, then use this data to support our process. Before we allocate it, every data here is unallocated. So they are unallocated data, okay? So when we have this unallocated data, we want to actually create allocated one, then it will become allocated one. But where is allocated? If it's a new one, we allocate it because we want to use it, so we allocate it. We will put it in the memory, physical memory, not disk. And this process is called cache it. Okay, so we got the data which is allocated and also cache it in memory. But if we don't use it a lot, for example, this data we just use it once, and after we finish this computation, we forget it or we don't use it like for a while. this data will be moved, will be translated to a disk. So if a data in a disk, they are still allocated data, okay? If the allocated data from the memory to the disk, we call it uncached. So the data still allocated, but it's become uncached. So this data is still allocated, but uncached. Okay, so you can see there's a three different kind of data in these systems. Unallocated data, they are new, just totally new. There's no this data created. No, they are not in the memory. Okay, they are not in the memory. They are not in the disk. There's a two kind of allocated data. One is in memory. We call cache it. We allocated a data and also cache it in memory. One is called uncached. They are reside like in a disk. We don't use it for now, but they might be used in the future. So we already create this data, but we don't use it for now, and we move it to a disk to support they might support the future like computation, but for now they just reside in a disk. So this data is allocated, so we have the data, but they are uncached. There's a difference between the data in these virtual memory systems. So hope you like today's video. Today we just briefly introduce what's a virtual memory, what's a physical memory, what's the physical addressing, what's a virtual addressing. Just keep in mind, because of the modern like systems, we want to do the multitasking. We want to support more process at the same time. So which means using a physical addressing is not enough. We definitely need one way to convert the address stored in your process to the actual address in your physical memory. But you can see there's so many different processes there. So sometimes we might need the disk or disk to support to do the secondary like a storage, right? To support these like systems. So in this case, MMU, this device is very important. It's hardware device decide for like do this transition from your virtual memory address to a physical memory address. This device help us to find the memory address on disk, memory address on physical memory, your RAM, DRAM, and so on, right? So it's very important. And if we have these systems, the data can be in unallocated data, so they can be just not allocated. Or if they are allocated, they can be loaded to a physical memory because we want to use it. So we load it to physical memory, which is called cached, allocated and cached data. If this data is stored on a disk, means this data did not be used recently. So because the physical memory is pretty full, so we need to put some data out to the secondary storage on the disk, right? So this data is called allocated because the data is there. So it's allocated data, but it's called uncached, allocated and uncached data. Okay, so I hope you understand the topic today. I hope you enjoyed today's videos. Okay, see you next time. Virtual memory is awesome.